Thank you very much for the invitation. So let me... Is this fine for everyone? Yes, no?
It's
Yes.
great, Claude.
Okay. So let me start with defining some spaces and metrics. So I will work with round M of L d lambda, which will be the set of exact closed Lagrangians in M d lambda. Okay. And sometimes I also use L0 of M d lambda, which is the set of L as above, which are Hamiltonianly isotopic to a fixed one. So such that L is phi h of L0. And usually L0 will be like the zero section or something fixed. Okay, so phi h is the Hamiltonian flow. So is my handwriting readable?
Yes, thank you.
Yeah. Okay.
Yes, very
good. The Hamiltonian flow of H. Okay. Now, I will also use the spectral metric gamma. And so this was defined in several ways. So there's a method using generating functions. And this was, I did that originally in 92. And so this works in L0 of T star n. And of course here L0 means those Hamiltonianly isotopic to the zero section. It was also done using Floer homology. By Leclerc, that was in 2008, and Leclerc-Zapolsky more recently, I think it was 18, and then it was done using, so that's on, sorry, that's on, whoops, L0 of M d lambda, which means that you define gamma of L1, L2 for L1 and L2 Hamiltonianly isotopic, and then it was defined using sheaves. This was done by Vichery in 2014, and this works in L of T star n. So you don't need to be isotopic to the zero section here. Okay. And the point is that they are all equal. This and this is something I proved for some of them in 95 and for other in 2019 more recently. So the connection between sheaves and Floer homology is from 2019, and the connection between generating function and Floer homology, of course, when they both define, is older. Okay, so what are properties of this? Just to remind you. Some property, well, the first is that it is a metric. The second one is that it is invariant by Hamiltonian maps, so that gamma of phi h L1 phi h L2 is equal to gamma of L1 and L2. Third thing is that it's continuous with respect to the Hofer metric in the sense that gamma of phi h of L and L is bounded by the C0 norm of H. And the last property, which is just a special computation, is that gamma of the graph of the F and the zero section is just the oscillation of F, which is of course less than 2 times the C0 norm of F, where graph of the F is just the set of x df of x, such that x is in N. And here, of course, I assume that when I consider cotangent bundle of N, you should assume that N is compact. So here N is a closed manifold. Okay.
Sorry, Claude, what do you mean by the oscillation of F?
Maximum minus the minimum.
Okay,
Maximum
thanks.
So, number of remarks here. Well, first is that you can do the same on the set of Hamiltonian diffeomorphism of M. Which I denote as d ham of M omega, and this was done by Matthias Schwarz in 2000, and Jongen O in 2008, I think. Okay. And this is just by considering, I mean, so you see Schwarz was actually before Leclerc, and this is, you can see it as just taking the graph of phi, so the set of points z phi of z, and look at this as the Lagrangian submanifold in M times M bar. Okay. And the second remark is that L gamma, so L is one of the above, is not complete. That will be the starting point somehow. Here it's not a complete metric space. Well, for example, if you look at a sequence Fn which C0 converges to F, where F is only C0, then the distance for gamma of the graph of dfn, graph of dfn, of course is bounded by twice the C0 norm between Fn minus Fn, C0. So the graph of dfn will be a Cauchy sequence for gamma, but it does not converge because it should converge to the graph of df, and the graph of df, if f is only C0, is not defined. Actually, it was, I mean, there was a question by Michele Stecconi. Is L gamma still a a Polish space or a bare space? I will just say a bare space. So it could be, you see, a space can be non-complete, but still be either a Polish space, which means by changing the metric but keeping the same topology, you can get a complete space, or just say it's a bare space, it satisfies bare property. In particular, if your space is already a countable intersection of open set in a complete space, then it will have bare property. So it's said to be a bare space. And somehow it's considered that if you have a bare space, there's no real point in taking the completion because that's already big enough and you already have enough points there. Okay. But the answer is no here. So that L gamma is not even a bare space. So let me go to the next step, which is to define the Humilière completion. So this was defined by Vincent Humilière in 2008 in his thesis. Oops. And this is just, I mean, the definition is just that we denote by L hat gamma and d ham. I'm sorry, I should have said that when I say d ham, I mean compact supported Hamiltonian in case m is non-compact. Okay. But the completion I denote by d ham without a c. So d ham gamma, the completion of the above spaces. And the goal, and this was in part done is in Humilière's thesis, is to understand L hat gamma or d ham hat of gamma. And I would like to make a remark is that these are not artificial sets, but elements of L hat gamma or d ham gamma actually occur quite naturally. Well, let me give you some examples. Well, the first example, of course, well, just take a C0 function on R, and you would like to say something about the graph of df, and this naturally belongs to L hat, but not to L. Okay. That's first example. A second example somehow is that, well, not L hat, but d ham hat occurs naturally when doing symplectic homogenization and this is a procedure where you start from a Hamiltonian on T star n, so you start from H, let's say smooth, in T star Tn R, and you look at hk of q and p, which is h of k times q and p, where k is an integer, and let k goes to infinity. And then if you want to describe the limit, it's described by some element which I denote by phi hat, which belongs to the ham hat. And you can start from an h which is as smooth as you want. You cannot avoid that the limit will be only in d ham hat. Okay. And a last case, which is the following. Assume that you have h c infinity in m minus v, so you take a Hamiltonian which has some singularities on a subset v. Okay. Then what is the meaning of phi h? Well, sometimes you can give meaning to phi h as an element in d ham hat, even though it doesn't have a meaning in d ham. So sometimes, and I will probably explain that at the end, one can give meaning to phi h in d ham hat. Okay. Okay, now let's try to advance on this goal here. And before I go to the next section, the further remark I want to make is that there are good news and bad news. So the bad news is the following, is that elements of L hat are not subsets of M, so let's say here M d lambda, and elements of d ham hat of M, let's say d lambda, do not act on M. So they are not spaces of maps. I mean, they're just abstractly defined as the completion of something. Okay, so they're Cauchy sequences up to some equivalence relation. Okay. And the relative good news here is that, however, you had an action of d ham over L by isometries, and so this goes to the completion because the gamma metrics are compatible. So d ham hat of M d lambda acts by isometries on L hat M d lambda. Okay.
Sorry, so bad news, it's a mathematical statement or just kind of...
That's a mathematical statement, yes. The last remark, you mean? The good news? The good
no,
news or the bad news?
No, good news.
Ah, the bad news.
Bad
Well,
news.
You like the bad news?
Yeah, so my question is, can you prove something, like, or formulate something? Or
Probably one could prove that the action of d ham on M does not extend to an action of d ham hat on M, but I haven't proved that.
I see.
But I think that's what you would like to. Maybe as we, from what I will say in what follows, it will, maybe a proof will appear by itself. I don't know. So,
Claude, is it? Did you think about introducing some natural objects in which you can view this completion rather than just viewing it as equivalence classes, or?
Not formulated this way, but I don't know. Maybe the sequel will give you some answers. Okay. So what I want to do is to take an element in this L hat and associate to that a set. So that's not very difficult. Actually, it was done, but in a different way by Vincent Humilière in his thesis. But the definition I'm giving is slightly different, and I believe maybe a little bit more convenient. Okay. So let L in L hat of M d lambda. So we say that X in M belongs to the gamma support of L if for any open set U containing X there exists some compact supported Hamiltonian diffeomorphism supported in U, by which I mean that the Hamiltonian is supported in U, such that gamma of phi LL is strictly positive, and this just means that phi of L is different from L. Okay. So it's quite clear what one means if you have a smooth Lagrangian L here. Okay, if you take a point here, well, you take a neighborhood, you take maps which are supported in this neighborhood, you apply this map to L, it's not going to move L. While if you are here, well, you just take a neighborhood and then you can just modify L to get something like this, and the blue one will be at certain distance from the black one. So you get actually a different Lagrangian. Okay, and of course this is for a smooth one, but you just take the same definition as for elements in L hat. So some properties here. Well, first, of course, if L is smooth, the gamma support of L is equal to L. Second thing is that this is invariant by d ham, not by d ham hat, because it wouldn't make any sense. Okay. So the definition of this gamma support, of course, if L is smooth, as I explained, it's just L. The definition is also invariant by d ham in the sense that the gamma support of I of L is the same as phi of the gamma support of L. And then there's some Hausdorff lower semi-continuity somehow is that if Lk gamma converges to L, then we have that the gamma support of L is a subset of the lim inf. So that's the lim inf for Hausdorff topology of the gamma supports of the Lk. And well, somehow the goal here would be to understand this, what is Gammasoup of L? Okay, what kind of set can you get? And so let me give. So this could be a first sort of general statement. And for example, if V is the gamma support of some L, some L0, how many L in L hat have the same support, the same gamma support? That could be, I mean, one of the questions. So let me give an example. So V will be the following. Well, here I have multiple points, and then I have a sequence Lk here as follows. And then I have another sequence, which I denote by L bar K, which is essentially the symmetric of this one. Okay. And assume that all this lives in T star of S1, so you just close up your curve. Okay. So the Lk converge to something which I will denote as L infinity. Here the L bar K. So L bar K is just the symmetric, obtained by symmetry by changing P to minus P from L. So this converges to something which I will denote as L bar infinity. And this is both the gamma support of L infinity, and it's also the same as the gamma support of L bar infinity. That's not very hard to check. Okay. So you see that you and the other thing is that if you look at the distance between Lk and L bar K, it's essentially, you can see it's essentially going to be the sum of the area here and the area. So this area, let's call it A, and this area, which is also A. So gamma of Lk and L bar K is roughly 2 times A. So L infinity and L bar infinity are indeed distinct elements in L hat. They have but they have the same gamma support. And what I would conjecture, but for the moment I don't know how to prove that, is that there are no other elements in L hat having this gamma support here. Okay. But at least this gives you an example where you certainly don't have uniqueness. Okay. So it's not something, I mean, completely. So now let's go to gamma-coisotropic sets. And this was essentially defined with a different name and slightly different definition, but really under the name of locally rigid by Michael Usher. So that was about, I think, 2018. So definition is slightly more complicated. Now I'm talking about subsets in a symplectic manifold. So V in M omega, and Z is an element in V. So we say that V is gamma-coisotropic at the point Z if the following holds: for any eta less than epsilon, there exists some delta strictly positive such that for, if you have phi, a Hamiltonian map compact supported in the ball of center Z and radius epsilon, and phi of V avoids the ball of radius eta centered at Z, then gamma phi is greater or equal than delta. So intuitively, what does this mean? Well, it means that if you want to move V outside of a small ball of radius epsilon, then you need a certain amount of energy. You could also say, what does it mean to be non-coisotropic, non-gamma-coisotropic at Z? It means that you cannot find a sequence which goes to the identity for gamma such that phi k of V intersection with the BZ eta is empty. Okay, here I forgot to put the empty set. Okay, so if you want to make a picture, here I have V. So here I have a ball of radius eta. Here I have, oops, sorry. Here I have V. Here I have the bigger ball. So this is B of Z epsilon. This is B of Z eta. And what I want to do is to move by a Hamiltonian isotopy supported in the largest ball, in the ball of radius epsilon, by a map phi. And if coisotropic means that gamma phi has to be strictly positive and bounded from, the gamma phi has to be bounded from below, and non-gamma coisotropic means you can find the sequence phi k going to the identity which relies this move. Okay, and let me state some properties here. Well, first, this is invariant by homeomorphism preserving gamma, hence by symplectic homeomorphisms. Well, this is quite obvious because the definition only involves open sets and gamma. So if you preserve both open sets and gamma, you will and well, actually that's the only property I wanted to state for the moment. So let me give some examples. Well, first, of course, if V is smooth and closed submanifold, then V is gamma-coisotropic. So when I just say gamma-coisotropic, I mean gamma-coisotropic at each point. So V is gamma-coisotropic if and only if V is coisotropic. The second thing is that if you look at 0, for example, in R2, of course, it's not gamma-coisotropic. And more generally, if S is codimension 2, at least 2, and symplectic, then it is not gamma-coisotropic. And the third case, which in a way is more interesting, is you look at 0, 1, the unit interval in R2, then this is gamma-coisotropic at Z, if and only if Z belongs to the open interval. So interior points are gamma-coisotropic, but the boundary points are not gamma-coisotropic. And that's also not hard to see, because if you have a point on the boundary here, okay, and you look at a small ball, it's easy to push this with small energy. While if you're in the middle and keeping the support in this ball, while if you're in the middle, you cannot do that. Okay. Okay, so I think it's time for a theorem. So the first statement is that if L belongs to L hat of M lambda, then the gamma support of L is gamma-coisotropic. And the second statement is, which I called piano Lagrangians, is that there exists L in L hat, let's say, of T star n, such that the gamma support of L is equal to the zero section union a cube and here n is the dimension of capital N. So on one hand, this support are gamma-coisotropic, and on the other hand, I mean, it's not that they are sort of Lagrangian in like C0 Lagrangian or something like that. Okay, they can actually be much bigger. They can contain, here if you take R equal n, they can contain a set of full measure. Okay, the set of gamma-coisotropic. And a remark is that for the case 2, there are actually infinitely many possible L with the same gamma support. Okay, at least if R is, let's say, for R strictly positive. Okay. So for example, if in the case n equal 1, so this is the zero section, you're going to just add a square where there are infinitely many distinct elements in L hat whose gamma support is given by this, the union of the zero section here. And this is, and the square. Okay. So this raises, I mean, it's always the same question, but for which V does the set of L in L hat such that the gamma support of L is V, a compact set in L hat. And usually I actually do not know the answer. Well, I sort of made a conjecture earlier when I had this sort of figure of 8. I said, well, I conjectured there are only two elements in L hat with singular support, this sort of figure of 8. Okay, but that's, and I also suspect that in this case here, in the case of of the Peano Lagrangians, actually the set of L is non-compact, but I don't have a proof yet. Okay. So let me go to the next question. So in a way, what's the feeling you could have is that when the gamma support is very large, then you will have lots of L with gamma support equal to this set, or at least contained in this set. And when the gamma support is small, then you have fewer of them. And the extreme case, of course, is what I call the regular Lagrangians, is what happens when the gamma support of L, let me write it as V, is a Lagrangian submanifold. And here I mean by Lagrangian submanifold, I mean smooth for the moment, at least. Okay. So the question you can ask, in this case, is it true that L is equal to V? So what does it mean? Well, V is a smooth Lagrangian submanifold, so this belongs to L, and a priori this belongs to L hat. But of course I have an inclusion here. So what this means is that the gamma support actually defines the element L in L hat. And another way to say that is that the L such that gamma support of L is equal V is unique. Okay. So there's one thing missing, is that I said if it's a Lagrangian submanifold, okay, but I should have added here exact. So in some cases, but not in all cases, one can show that the gamma support, if it's Lagrangian, is automatically exact. Okay, but in some other cases, at least I don't know how to prove that. But let's assume that this is the case. Then this is the question. So another theorem says the following. So the assumptions on L is not the most general one, but so let N be a compact homogeneous space, and assume that the gamma support of L, which is V, is, well, exact and Hamiltonianly isotopic to the zero section, so it's in L0 of T star N, then the gamma support of L is indeed equal to L. So in this case, I can actually prove this. I mean, there's a bigger class of manifolds for which this works out, okay? But there's no point in giving the most general assumptions. So this also has some number of consequences. Oops. Well, for example, one question which is not completely obvious is, what is the center of the Ham hat? Okay. And the theorem implies at least that for d Ham hat of T star Tn, the center is trivial. We expect, I expect that this is always, that this should always be true, but I can only prove it in this setting. And probably it's the right moment to ask if there are questions. No questions? Okay, so let's move to other applications of this. So the first one I evoked at the beginning is about singular Hamiltonians. So the question is, if you have, for example, a Hamiltonian H in C infinity of M minus V, does H define an element phi H in d ham hat of M? Not of M minus V, of course, but of M. And well, one can write a definition. I mean, maybe I have too many definitions, but that's maybe we'll clarify things. So we say that V in M is F coisotropic, so F is like function at Z in V if the map from d ham of M, so the restriction map here is onto, here U is a neighborhood of Z which is small enough. Okay. On the other hand, anytime you have a Hamiltonian defined in M minus, so let me maybe make a picture. Here I have V, and I want to localize things, so I have Z here, and I take a neighborhood here, and they say, well, whenever I have a Hamiltonian which is defined here, in the complement here, and locally here, then I can extend it to something which is defined everywhere.
What?
So let me state again a theorem.
So this question, where is F figuring in this definition? Because it was
Sorry?
It says it's F coisotropic, and then I don't see F.
At Z, at the point Z in V. So
F coisotropic is just a term. I thought F was some function. Okay.
Sorry, and what is written? I cannot read. M comma U intersect V or M minus U intersect V.
M minus U intersect V. So you remove this. This is U. So you remove U intersection with V, you remove a small neighborhood of Z in V, and you have something which has a singularity on V near Z, and then this object can actually be extended to F.
Sorry, but I'm not sure I understand the definition. So M minus U intersect V is not an open set, right?
No, maybe you want to you want V to be closed. You're right, and you could take the closure here if you it's U inter V is locally closed, and then I mean, either you define what d ham is in this case, or you just take the closure here to get an open set. You could do that if you want.
And then I consider compactly supported in this set, kind of. So d ham.
Yes, you consider Hamiltonian which are supported and only have singularity on this small black, on this thick black black region. And if for u small enough you can extend, then you're f-coisotropic there.
Okay.
Okay.
Still, can you explain this again? Because I would be sort of good to know what the set is there and what is the precise definition then of which I take the completion. I think Leonid has the same problem.
You could,
so you tell us precisely what you take, and then we are happy.
So I take V to be closed, okay? So here V is a closed subset, okay? And sorry, just a second. I think I actually got confused here. Because this is the definition of being not coisotropic. Sorry. So it's not F coisotropic. And so if you don't like taking the so d ham of M minus an open set is a symplectic manifold, okay? If you don't want to take care of the completion, you just take d ham C, okay? If you don't want to go to the completion on the right-hand side, okay, that it's not going to change anything. Okay. But the condition is that any element which has a singularity on this set here can actually be lifted to an element in the completion here. So having a completion on the left-hand side is mandatory. Having a completion on the right-hand side is not. Does this answer the question, or?
Well, it's getting better.
Okay.
Maybe I have a follow-up question, because I'm a little bit confused why completion on the right-hand side is defined.
Okay, let's. Is that better?
This is much better.
Okay, that's fine. So, so the theorem is that if V is nowhere gamma-coisotropic, then it is, and this is also true at points. So it's nowhere F coisotropic. And the corollary of that was actually proved by Vincent Humilière a long time ago, which says that if the dimension of V is strictly less than n, and V is smooth, then any Hamiltonian defined, let's say, on even C0 on M minus V defines an element in d ham hat of M omega. Okay. And somehow that's, you can see this theorem as an extension of Vincent's theorem. So that's one kind of application. So let me go to a second type of application, and this is joint work with Stéphane Guillermou. So if you take an element in the Rife category of n, then it has a singular support. And this was defined by Kashiwara and Shapira, who also proved that SS of F is, well, what they called involutive. So this is a condition on the tangent cones of a set. So you say that a set is involutive if, so there are basically for a set you can define a large tangent cone and a small tangent cone. And the set is involutive if the orthogonal of the linear span of the big one is contained in the small one, the small tangent cone. Okay. So that's a condition which is invariant by C1 map or maybe by Lipschitz map, but not much more. Okay. So the theorem we prove with Guillermou is that actually the singular support of F is gamma-coisotropic. And the remark is that this implies, so gamma-coisotropic implies involutive. And there are examples of involutive sets which are not gamma-coisotropic. This being said, for the moment, we are not extremely happy with the example we have, which are essentially products of counter sets. So there should be better sets. Okay. And the last thing, I think I have a few more minutes, is joint work with Vincent Humilière. So let phi be a map from symplectic manifold to itself, which is, well, what people call dissipative, or which is the same conformally symplectic, which means that phi star of omega is C times omega, where C is contained between, strictly contained between 0 and 1. Okay. Then phi induces a map, well, from L to L, which is contracting for gamma, and so it defines a map from L hat of M d lambda to L hat of M d lambda, which is a gamma contraction. And since these are complete spaces, and this remark is due to Marie-Claude Arnaud and Vincent Humilière. So let's call it phi again. So this has a fixed point in L hat of M d lambda. Okay, you have a fixed point in some completion. That's maybe not so helpful, but then you can think of the gamma support. So as a result, phi preserves the gamma support. Let's call this L infinity of phi, which I will call as V infinity, let's say, of phi. Okay. And so this gives you an invariant set. Okay. And what happens, what is this set when n is equal to 1? Okay. And if I'm working in T star of S1, well, this was actually figured out by Birkhoff in 1932 by Marie Charpentier. Marie Charpentier in 34, and you can read about it, and it was also improved in paper by Le Calvez between 86 and 91. So what happens here? Well, you can look at the map phi and say, well, this map phi will send S1 times minus m into itself, and then I can find an invariant set which will be the intersection of the phi n of S1 times minus n. And this is the picture which I represent here. Okay. So inside the blue region is phi n of S1 times minus mm, and when you take the iteration, it will go in, it will be preserved, so you get thinner and thinner set, okay? And in the limit you get this black set. Okay. Now from the above you can say, okay, this black set cannot be gamma-coisotropic. Okay. Well, why can't it be gamma-coisotropic? Well, because if you look at the point here, for example, well, this looks like the endpoint of the interval 0, 1. And we saw that the endpoint of 0, 1 is a point where the set is not gamma-coisotropic. Okay? But that's not what Birkhoff or Charpentier do. What they do is the following. They said, well, you have these leaves here somehow, and you can cut these leaves and get a smaller set. So this is called the Birkhoff attractor. It's a little bit of an abuse of language because some points do not go to the Birkhoff attractor. Somehow lots of points end up on the Birkhoff attractor, but not all of them. But it's still called the Birkhoff attractor. Okay. Well, what happens is that the Birkhoff attractor is exactly, so this is exactly the gamma support of L infinity of phi. So this L infinity of phi gives you a high dimensional generalization of the Birkhoff attractor. And I think my time is up. I'm sorry for, well, I don't know if I was over time, but sorry for the issues, and thank you for your attention.
Thank you very much, Claude. Excuse us for the interruption. I mean, you dealt with it very well, Claude. I think it's more of a problem sometimes with these Zoom things. In any case, are there any questions?
I have a quick and possibly very naive question. Claude, is it clear that the gamma support is non-empty?
Yes, there are many properties. I should have talked about that, but the gamma support actually, for example, if you have two Lagrangian L1 and L2, the intersection of in T star n, the intersection of their gamma support is always non-empty. Also, the intersection of the gamma support with the vertical is always non-empty. So in fact, it's quite easy to construct gamma-coisotropic sets, just take smooth coisotropic sets, which cannot be gamma supports just because they don't satisfy these intersection properties. Okay.
I see. Thank you.
Okay. Thank you very much. Are there maybe other questions?
Should I stop the screen sharing?
Just a second, because there's some movement in some rooms. I don't know if this indicates questions coming or no. Okay, yeah, I think it's possible, Claude, to stop the screen sharing. All right, so
okay.
Okay, so maybe I will ask a question still.
Yes, of course, of course.
Yes, so you mentioned this result about center of the completion. So
About what?
the center of the completion of Hamiltonian diffeomorphisms of
Yes.
T star T. Okay,
Yes.
so can you briefly indicate the idea of the proof?
Yes. So the first thing is that you can show that the gamma support should be either the diagonal or everything. Okay. But because you assume it's compact supported, you can remove that it's everything. Okay. And then you somehow are reduced to the theorem about regular Lagrangians, which will tell you that if something has gamma support, so that's why it works with T star Tn, because you can, up to a covering, you can replace T star Tn times T star Tn by the cotangent bundle of T star Tn itself. Okay. And so you can reduce yourself to a case where you need a compact homogeneous setting, and you can then say that the gamma support is L. So there's a unique element having this gamma support, and this means there's a unique diffeomorphism having gamma support the diagonal. And then
and this is true for torus or for homogeneous spaces? Or, I mean, what is the generality?
It's true for torus, it's true for T star Tn, then it's not, this particular proof, I don't know how far it extends. I'm not sure, because you need to get back to a cotangent bundle of the diagonal somehow. And
I see.
I don't think that besides Tn, T star Tn, you can do much more with this method. Of course, I expect that it should be true. In general, I mean, it follows from the general conjecture that a regular Lagrangian is unique. If you have that, then you just apply it to the diagonal, and you prove that that the center is the identity. But without the proof of such a conjecture, that's all I can do.
Okay, thank you very much.
Thanks.
Thank you. Maybe there are other questions. See, okay. If not, we can thank Claude again.
Well, thank you.